now we resume our morning session, and Henry will continue our discovery, and now we'll give a few glimpses into this very nice recent result, and I can start.
Okay, welcome back. So this is part 2 of the talk, and let's jump back into rigidity. So testing for many qubits. So I described one test, which is this simple, repeated magic square game. Okay, you play it n times. It's very nice. It certifies 2 EPR pairs, and on every EPR pair, you're performing X and Z poly measurements. Okay. But what are some of the other parameters? Well, in this particular protocol, the message lengths, the question and answer lengths, are order n bits, right? Because you're playing n copies of this magic square game, and also we kind of talked about this. What is the robustness of this game, as far as we know? So, if you're winning with 1 minus epsilon probability in this repeated game, then we can only guarantee that you're n squared, square root epsilon, close to this ideal strategy. And this is not very good, because the more EPR pairs you're trying to certify, in order to guarantee anything, your winning probability has to get closer and closer to 1.
What does close mean in this context?
Oh, good. So it means that the technical definition is that they have some quantum strategy, so they share some state, they have some measurement operators. It means that there's some change of basis, local change of basis, such that under that change, it is in Euclidean distance close to, say, EPR pairs, 2 n EPR pairs, and the measurement operators are this close to the actual poly operators. I mean, operationally, it says that you cannot distinguish between the two strategies. It's technically in terms of, it's a state-dependent distance. So their action on the state is this close. All right, so you can hope, is there a better test for many qubits that's more robust, maybe shorter question and answer lengths? And it turns out that there is, and this is the state of the art. This is the quantum low degree test invented by Natarajan and Vidic. And parameters are much better. It certifies n EPR pairs, okay? Also X and Z poly measurements on those EPR pairs. And now the question and answer lengths are exponentially better. They're polylog n bits long, okay? So very short. And the robustness is also much better. If you're winning with probability 1 minus epsilon, then the closeness guarantee is only a function of epsilon. There's no n dependence. So it's epsilon to the alpha, where alpha is some constant, like 1 over 8 or something, close to the textbook strategy. This is very nice. That means the more EPR pairs you want to certify, you don't pay any price in terms of the robustness. And this is sort of the frontier. And I mentioned earlier that whenever we had an advance in proving a better rigidity result, we get better multiprover protocols. And that's the case here. Let me actually, to sort of, I won't describe what this test fully looks like, but to give you sort of an idea, it actually relies on something from classical theoretical computer science in a very important way. And it's something called the classical low degree test. Right? And this is somewhat fascinating, because this was invented in, way before we started thinking about quantum multiprover proofs. It comes from the 90s. And it's a protocol with what I'll call classical rigidity. So here now we're going to think about the classical setting. There's no entanglement. Provers are deterministic. Yet there's still some notion in which we can enforce structure on the behavior of provers. This classical low degree test is crucial in something called probabilistically checkable proofs, or PCPs. And what is this test trying to do? It's trying to test whether the responses of the provers are consistent with a low degree polynomial. Okay? So in particular, a low degree polynomial over some finite field, okay? Over m variables. Right, so what does this test look like? Well, we have these two boxes. They're no longer sharing entanglement. They're just deterministic. And we're thinking about vector spaces over this finite field, f to the m. So here's what the verifier does. It picks a random point, x, in f to the m. Okay, it's going to send it to one of these boxes. And then it's going to pick a line, L, that goes through this point and send this line to the other box. And this box doesn't know what line L is, and that box doesn't know what point X is. And the prover A will respond with some f of x. F is some arbitrary function that we're trying to determine if it's close to a low-degree polynomial. And the prover B will respond with a univariate polynomial along this line. It's going to be degree D polynomial. And think of D as very small, some, I don't know, like 3, for example. And they give these responses, so this is a value in this finite field, and that's going, R sub L is a low-degree polynomial. The provers win if, when you evaluate this univariate polynomial at the point X, it agrees with the response of the first prover. This is the classical low-degree test. Well, what do we know about it? Okay. So what is this R sub L supposed to be? If f is indeed a low-degree polynomial, it should be the restriction of f along this line. So here's the amazing classical rigidity theorem. Okay. If these classical provers win with probability greater than 1 minus epsilon, then in fact this function f, right, the responses of this black box is going to be close to a degree D polynomial. And this is somewhat amazing because it's an extremely efficient test for structure. Right? So if you think about the description of this multivariate degree D polynomial, how many degrees of freedom are there? Well, it's given by this binomial coefficient. And if you think of m and d as growing parameters, then this is something that's exponential in m. Okay? Right, so that's sort of the description length of this low-degree polynomial. But as a verifier, we're ascertaining that it has this low-degree structure just using very short messages. To describe this point x, you only need sort of n log f bits of information, and not much more also to describe this line. So the verifier is only seeing very small glimpses of this function f, yet by playing this game, it's able to determine that globally it has this low-degree structure.
So does the O of epsilon depend on like field size and D?
Oh, yeah, I think there's some lower order terms in terms of the field size. If like D over Q is very small, then like sort of going to 0, then I would sort of ignore that.
Okay.
Yeah. So this is the classical low-degree test, and it's very important in classical complexity theory. And it turns out that we can use the same idea. Even though this is a purely classical result, we can use it to establish structure very efficiently in the quantum setting. And this is what's used for the quantum low-degree test. Right. But even before that. So imagine we play this same classical test where x and L, we give it to these two boxes, but now we assume that now the provers can be quantum; they share quantum state. So this box is no longer deterministic, and it's making some measurement on some state to produce its answer. We can still say something very interesting about their behavior. This is the quantum analysis of the classical low-degree test. So if the provers are winning with high probability, then in some sense that I won't make formal here, their measurements are actually consistent with measurements that produce a degree D polynomial. So roughly speaking, however these quantum boxes are behaving, you can think of them as having some degree D polynomial in mind. So this classical rigidity phenomenon persists even in the presence of entanglement. So it's something really remarkable about this low-degree test.
You might have said it previously, and I might have missed it. Can you just comment on the alpha?
Oh, I think of it, I'm not sure what the constant is. It's like 1/8 or something.
Okay, thanks.
But is it some like non-commutative polynomial or like an actual?
Oh no, just over a finite field. It's f, mapping fn to f. I mean, so here, I mean, these responses are still finite field elements, and we're trying to determine if the map from x to a, in some sense, is it coming from evaluating a low-degree polynomial at x.
But you were saying, I mean, the responses are not deterministic, at least for x. So like, what function should I mean, forget.
Okay.
Like, what function
Okay.
should I be thinking of?
So what's really it's saying that without loss of generality, the strategy looks like this. The provers ignore their inputs. They make some measurement on, say, some state. From this measurement, they extract a description of a low-degree polynomial f. And then they evaluate their questions at that low-degree polynomial. So it's sort of like they first use shared randomness to get a low-degree polynomial.
Okay. Okay.
And then they ignore all their quantumness and just play with that low-degree polynomial. Good question.
So does that mean, does this use the entangled state just like those quantum fingerprinting does to replace shared randomness? In the simultaneous message passing protocol, one can often use replace shared randomness with an entangled state. Was what Harry Bremen and Ronald DeWolf were trying to assert a number of years ago. Is this another example of that?
This would sort of be like the opposite. It would say if they had an entangled state, they're not using it for any real quantum reason. They might as well just have used shared randomness.
Oh, I see. Interesting.
Yeah. So the formal statement is that if there is an algorithm, there's a pair of provers that win in this game, then there's a pair of provers that do exactly what you said.
Almost. I mean, morally speaking, yeah.
But the measurements don't depend on the questions, right? In this sort of other game.
Yes.
So why can't they just sort of share randomness and
That's essentially what this is saying.
oh,
Yeah.
and that cannot happen by the old low degree test soundness, and that's that.
Yeah.
So I guess you take whatever strategy they have and then you extract like this other strategy
Right.
that is much simpler, that does just as well.
Mm.
Yeah. So I think this is really a remarkable thing that even you can first classically that you can establish substructure and that even when the provers are quantum, you can still say something like that. Okay, so this is the classical low degree test. And now how do you go from this classical to quantum low degree test? Well, I'll just give you sort of like a very impressionistic picture of what's going on. So here we want to certify not a low degree polynomial, but the fact that these two boxes share many EPR pairs. So very roughly, the verifier will perform the classical low degree test in two different bases, complementary bases, the x and z bases. Okay. So it'll say, I'm going to play the x basis, let's play the classical low degree test. Or maybe I'll play the z basis and play the low degree test. But now we have to relate the two, and this is where we use the magic square game to actually tie these two bases together. And turns out that you can do this, and this is enough to certify many EPR pairs very efficiently. So I won't say much more about this, but this is sort of the rough idea. Okay, so we have this quantum low degree test. It's very efficient. Now what can we use it to do? So now I'll turn to the complexity of interactive proofs with entangled provers. So we're back in this interactive proof setting. And recall that the provers want to convince the verifier of some statement x. N is the product of two primes, some circuit accepts with high probability, or things like that. Maybe two graphs are isomorphic. So what sorts of statements can be verified using a multiprover protocol with entangled provers? Here we're going to make no assumption on the complexity of the provers. Right? They're allowed to be as powerful as they want. They can solve even unsolvable problems. We grant them that. The constraint is that they must obey quantum mechanics and they cannot communicate with each other. And we want to have a protocol that's complete and sound, as usual. So classically, this question is not new. People thought about this in the classical setting if we had two classical provers, and we can describe the set of problems that can be verified in this model as MIP, multi-prover interactive proofs. We think of the classical provers as deterministic, and one of the gems of complexity theory is this result of Babai, Fortnow, and Lund, who showed that the class of problems that you can solve in this model that you can verify in this model is exactly NX, non-deterministic exponential time. So, if you're not a complexity theorist, it means that you can check pretty extraordinary statements. A polynomial time verifier can check whether some Turing machine outputs 42 after taking exponentially many steps. So clearly, this polynomial time verifier can't check this on its own, but by interacting with these provers, it can check such a thing.
Only two?
Only two.
Only two. So 3 doesn't help.
3 doesn't help.
But it's important that it be interactive, so more than one round.
One round's enough.
Oh, one round.
I think there's even there's a paper called like 2 provers, 1 round, 0 knowledge for ADX. It's a magical thing, but where does the magic come from? It comes from this classical low degree test. It's amazing. So this is a gem. It led to many things in complexity theory, PCPs and so on. So now back to the quantum case. These 2 provers share entanglement. We denote the class MIP star. Right? This is a set of problems that can be verified in this model. How do these 2 models compare? What is the relative power between MIP versus MIP star? So to do this comparison, let's first think about a classical MIP protocol to verify some statement X, right? A protocol that Babai, Fortnow, and Lund came up with. So with entangled provers, if we ran this classical protocol, then if X is true, then we have no problem. These provers can just ignore the fact that they were quantum, just behave the same way that the classical provers did, and just prove to the verifier that X is indeed true. So that's not a problem. But what about if X is false? So in the classical setting, BFL proved that the verifier rejects all classical provers with high probability. But what about entangled provers? Maybe there's some correlations that this entangled state could allow the provers to send responses that fools the verifier. Right? This is something that we're worried about, whether the soundness condition is preserved. So a priori, the soundness of these classical protocols may no longer hold against entangled provers. So the first breakthrough about MIP star came in 2012 by Ido Vidic. And they showed that soundness can be preserved. At least all problems that can be verified in the classical case, NX, can also be verified with entangled provers. And the way they did it was actually they looked at this protocol of Babai, Fortnow, and Lund, and they said, it's still safe against entangled provers, right? And it comes from this guarantee about the classical low degree test, right? I mean, I sort of told you that if you play this low degree test, there's no reason for the provers to use entanglement, right? Entanglement doesn't buy them anything. So you kind of plug that in and you argue that this BFL protocol is still sound. These provers cannot trick a verifier. Right? So the upshot is that entanglement cannot reduce the complexity of multi-prover protocols.
So what's the difference in between like what is proved in this result and the 2018?
Oh, they go hand in hand. Oh, I see. So this 2012 result proved qualitatively weaker, like it had more provers, the parameters were worse. This 2018 result sort of proves the two-prover version of the classical loaded retest.
Ah, I see.
Yeah. All right, so it cannot reduce the complexity. Now you can ask, well, can entanglement expand the complexity of MIPs? And this is where things get really fun. Another way of thinking about this question is, are there any algorithmic upper bounds on MIP star? Right. So, what does this mean? Well, as a comparison, let's think about the argument in the classical case. Classical MIP has an algorithmic upper bound, right? A crude upper bound is any problem that you can verify in MIP, you can solve in doubly exponential time. Right? So here's a computer. It gets some statement, is X true? And all we know about X is that it's some statement that could have been verified in the classical MIP setting. Right? But this computer doesn't have access to provers, so it just has to solve it itself. What it does, it sort of simulates in its head this MIP protocol. Right? It's going to enumerate over all possible provers, deterministic provers, and calculate the acceptance probability of the verifier. And it uses the completeness and soundness guarantees of the original classical MIP protocol to figure out whether X is true or not. Right, so if X is true, then there eventually will hit upon some provers that cause this verifier to accept. Otherwise, the verifier will always reject. And this takes only doubly exponential time. There's only that many provers.
In fact, even singly exponential.
What's that?
So with singly exponential with non-deterministic.
Right. Yeah, so that would be a tighter upper bound, yeah. So why doesn't this work for MIP star? Well, when you're thinking about quantum provers, what does it mean to enumerate overall prover strategies? Well, you have to enumerate overall possible quantum states, all possible measurements. First of all, this space is infinite. But moreover, it's not infinite just because it's a continuous space, but how many qubits of entanglement would the optimal provers need in such a protocol? Right? Do they need 2 qubits of entanglement, 100 or a million? There's no a priori, there's no finite upper bound on the amount of entanglement needed for provers to play in this protocol. And in fact, because of this reason, there is no reasonable upper bounds known on the power of MIP star. Right? There's no algorithm that could capture this class. And so the best upper bound that one could place is RE, which stands for the class of recursively enumerable languages. And this is a class that includes the halting problem, for example. Okay. So if you can solve the halting problem, then you can solve problems in MIP star. And the result that we recently announced is, in fact, this upper bound is tight. Every problem that in RE, including the halting problem, can be verified with entangled provers. So, so it gives an explanation for why people failed to find an algorithmic upper bound for this class. So what are the complexity theoretic implications of this? It's kind of crazy. If you have a classical polynomial time verifier interacting with entangled provers, it can verify statements like X, which is some Turing machine M eventually halts. We don't know when it halts, but if it does eventually halt, the provers can prove this to the verifier. And this also means that there's no computable upper bound on the amount of entanglement needed to, in general, MIP star protocols. And again, that means there's no computable upper bound on MIP star. Okay, so how is this possible? Well, I'll describe sort of a result from last year, which really contains the essential idea for this, which is due to Natarajan and Wright. The result that non-deterministic doubly exponential time, NEXP, is contained in MIP star. And this result shows how verifier, this polynomial time verifier can use entangled provers to its advantage. And the key idea is, of course, to use rigidity, to force provers to simulate an exponentially large verification protocol. Okay, so how does that result work? I'm going to give sort of a sketch of it. Our goal is, suppose your goal was this. You want to verify some statement x. A Turing machine M halts after 2 to the n steps, just exponential time. This statement x is an NX statement. So using the result of Ito Vidic from 2012, this means that there's an MIP star protocol, has 1 round. The verifier runs in polynomial and n time, and it's based on the classical low degree test. We know this from 2012. All right. Now what if you're more ambitious? You want to verify a harder statement. You want to verify that a Turing machine M halts after 2 to the n steps. Well, just almost trivially, I mean, what's the difference between 2 to the n and 2 to the n? I mean, we can just use the same protocol from before. I'm going to call it protocol P big. It's 1 round. The verifier now runs in 2 to the n time. I've just sort of blown up the verifier. And it's based on the classical low degree test. Of course, the verifier doesn't have this much time to run in real life. What we want is a protocol P small that verifies the same statement using a polynomial time verifier. So how do we do this? Well, it goes in 2 steps. There's a question and answer reduction. So we start with this big protocol. It takes a long time to run, and the questions and answers are exponentially long. The first step is to reduce the size of the questions. So we're going to get an intermediate protocol, pint. The questions are shrunk down to polynomial size. The answers are still really large. But then we do a second step where we shrink the answers. So the questions and answers are both polynomial time. And this is our final protocol, P small. So those are the 2 steps.
Should we think of P big as like, this is like all of the internal states of the Turing machine, or like how should I think of P big?
Oh, good question. So P big doesn't actually capture, I mean, remember, we're trying to verify whether a 2 to the n computation halts. So there's not even enough time. The answers won't specify all of that. You're only getting these small views into it, but you're using this PCP-like technology to certify it.
Yeah.
Okay, so how do we do this first step? How do we reduce the question size? Okay, so I said that this big protocol relies on the classical low degree test. So we have these 2 provers. In P big, it's going to get a point and a line. The description of this point and line are exponentially large, right? So we're going to create an intermediate protocol, pint, where instead of generating, instead of the verifier generating this point and line by itself, it's going to ask the provers to do it for the verifier. Okay. So it's going to run some protocol using very short questions, and it's going to ask the protocols, hey, not only do I want you to answer, come up with an answer, I want you to generate the question yourself. Okay. I don't have enough time to do it, why don't you do it for me? And this is the technique that Natarajan and Wright call introspection. Right? You're getting the provers to ask themselves the questions. Of course, why would the provers cooperate with you? And this is where the magic happens. So this is how this introspection protocol works, pint. With probability half, you run this quantum low degree test. You ask, you certify that they have exponentially many EPR pairs. Okay. But since the quantum low degree test is so efficient, the sizes of the questions needed to run this protocol are only polynomial length. So you can do that efficiently. So you run this quantum low degree test, you know what they're doing, they have these exponentially many EPR pairs. And then with probability half, you're going to run this introspection protocol. going to run some interesting procedure to ask the provers to sample from this point and line distribution. The same distribution as occurred in this original p-big. And then you say, well, once you've sampled these questions, answer those questions.
So in T-big, the protocol had exponentially many EPR pairs. That's the, I mean, in principle, they could have had many more, but but the protocol actually.
Yeah, so they could have many more, but you don't know anything about it. This is to establish, here's some structure, yeah.
So the questions that the answers that you're receiving are already even too big for you to read efficiently, right, in the introspection stuff?
Yeah, so the answers are still very large.
Okay, good.
Yeah.
Okay, good.
We just want to reduce the question sizes first.
It's not clear to me a priori that these two are indistinguishable. They still need to be right to the provers. So that is, with probability 1/2, you do the low degree test, and it should be indistinguishable from the introspection protocol.
Right.
But the introspection protocol has different outputs. It looks like.
Great. Yeah, so I'm glossing. There is a way to interleave the two protocols so that they're indistinguishable at the right moments.
Right moment. Okay.
But so you can sort of imagine that there's in a similar way you can sort of, I mean, actually there's several intermediate games that you use to this game from one perspective, from one prover's perspective, is indistinguishable from one game, and then you kind of chain a bunch of games to connect the two.
Okay. Did you give us any details on how the introspection, keeping the prover honest?
No, I'm going to give, fortunately, no details about that. Yeah, so there's a lot of cleverness in there. But this is more of a high level. Good. So this p-int, you certify many EPR pairs. The EPR pairs are going to be the source of randomness to generate this x and L, okay, according to the right distribution. And yeah, it's very challenging to somehow force these provers to really sample. You want to say that this prover only samples X and learns nothing about L, right? Even though they're using the shared EPR pairs. So you have to somehow force this prover to not learn anything about L. And you have to design a protocol to do that. And the same for this other prover. But in the end, they do get this X, and that only gets L, and then they respond with. And this is, the fact that this works is really miraculous. I mean, at least the solution we know of today on how to do this really relies on the special structure of this point line distribution. If it was some other test used in this classical MIP protocol, it's not clear we would have been able to get the provers to do this introspection. So there's something really remarkable. Maybe we're lucky or something. But this works because we're using this point line distribution.
Just out of curiosity, like, if you receive this this answer to please generate these exponentially large questions, even if I were allowing the verifier an exponential runtime, what would like a bad answer look like?
Right.
Or like what would he not accept?
Oh, good. So this goes back to this, how do you tie together the quantum low degree test with this introspection? So, actually there's many more tests, right? But the introspection one, once you get to that point, you sort of trust that the provers are doing the right thing.
Okay.
And it's sort of, how did you get from enforcing that they're doing X and Z measurements on EPR pairs to doing the right thing? And that's what all the intermediate tests, you establish one foothold and then.
And this will be at least two rounds of interaction?
One round. It's only one round here. Don't worry, it's only going to be one round. Yeah. So, and eventually zero knowledge. Okay, so good. So we've done this question reduction. Now we have to shrink the answers. And here I'm just going to go through it at light speed. I'm not going to explain anything here. But there's the final P small protocol instead of giving this XA and LR, we're going to give these short polynomial-sized proofs that they would have given you the right answers. So they give these short proofs. These proofs are based on the things I mentioned earlier, these PCPs. So they're short, you can verify them efficiently. And essentially, what's happening is this, the verifier doesn't have enough time to check this XA and LR. It says, well, provers just prove to me that I would have accepted if I had the time. So that's what this
So this doesn't seem like a black box use of PCPs, right? Because the provers don't even know the statement.
Yes.
PCPs, you and I at least know the statement, yeah?
Yeah, so there's another trick in which we actually, before this step, we ask one prover to play the role of two. And then the other prover to check consistency.
Okay, got it.
So this prover now knows the full statement. Yeah. So this is this irregularization.
Right.
Okay, so we've shrunk the questions, we've shrunk the answers, and now we have our polynomial time protocol. But we verified this incredibly complicated statement. This Turing machine accepts after doubly exponential time. And we've checked it in poly. And sort of to recap, really, what's the foundation? It's this quantum low degree test. And you're using this introspection protocol to certify sampling from an exponentially large classical low degree test. And we use this PCP technology from complexity theory to reduce the answer size. Okay, so just to put it in terms of pictures, here's the schematic. We have this polyentanglement verifier. We run this quantum low degree test to certify exponentially many EPR pairs. And these EPR pairs are generating questions for this point in line distribution. And this point in line distribution is used to certify that there exists some doubly exponential size low degree polynomial out there. Okay. What do I mean by out there? Like, out there as in this low degree polynomial is encoding the answer to our computation, this doubly exponential time computation. Okay, so that's in one picture how NEEXP is included in MIP star. So why not iterate this process? Why just stop there? And indeed, why not run a quantum low degree test and get the provers to generate the questions for another version, round of the low degree test, and have them answer that, and just continue this to certify that the provers had more and more and more and more EPR pairs. And that's what we do. So you can recursively iterate this introspection technique by Anand and John, and it yields an MIP star protocol for verifying the halting problem.
The soundness error is not a problem, the soundness error for the NEEXP protocol
Right.
is a constant, you're saying?
Oh, but we can reduce the soundness error using parallel repetition. Yeah. Because we're only dealing with constant error in each step.
So when you just to remind myself, when you say the halting problem, for example, we don't specify an upper bound on the running time, right? So yeah, exactly. Like how does the verifier even decide how many iterations we're going to do this, right?
It doesn't. It says provers figured out for me how many iterations.
With one round of communication.
Two. No, it's just one. It's one round. It's one
Really
round.
two?
It's one round.
No. I'm never kidding.
Okay, the provers figure out how many iterations to apply, then they have to tell the verifier?
Right. I mean, because the number of iterations could be, some crazy busy beaver 10 or something. But through these PCPs, they sort of prove that you did each
Here's my question. What's the verifier actually checking? Is there a way to...
2 rounds of the iteration. Yeah. Okay. So.
Then it's clear, like any number of rounds.
Yeah,
it's clear what
the infinite, yeah.
Yeah, that's the part
I don't have a good answer for that. Yeah. I'll try to describe it to you offline. Yeah.
Aren't you testing if the other level are testing the right thing? Somehow you're just...
Yeah, it's sort of like actually that's a good way. It's like an inductive thing. You're sort of testing that they could have proved that all the previous levels were properly tested for. And then, sort of like an inductive proof.
Oh, okay. For example, how many qubits does a probe need to share? Is it singly exponential or doubly exponential? Or
Singly exponential. Yeah. So that actually gives us sort of a tight. So if you limit the provers to sharing, q qubits, then 2 to the q qubits, then q qubits, then they can do n time 2 to the q.
Right.
Okay, so this is all very vague, but that's sort of the general gist of the idea. And it's very interesting that this undecidability or uncomputability result has some very interesting consequences. I mean, not only for complexity theory, showing that this class contains undecidable problems, but also some other problems in seemingly different areas, such as in mathematical physics, there's something known as Searlson's problems, and there's also there was this open problem called the Kahn embedding problem from the theory of operator algebras, and this complexity result actually shows that the answer to these 2 questions is no. And I guess I won't have time to really go too much into it, but I'll sort of show a slide about it. There's these 3 problems, and one of them has been around for quite some time, and the other 2 are more recent, but they all are very closely connected. So this Kahn embedding problem, it's from pure mathematics, and the formal statement is this. It says, do all separable type 2-1 factors embed in an ultra power of the hyperfinite 2-1 factor? It's some statement about von Neumann algebras. It's very deep. And over the years, people have discovered that this question is equivalent to many other questions in mathematics that have seemingly nothing to do with operator algebras. One of the equivalent formulations is the Searlson's problem, and it asks, it's something closer to our world, are all quantum correlations in this commuting operator model, so it's some mathematical model describing quantum correlations, are all of these approximable in finite dimensions? And this complexity question, is there an algorithmic upper bound on MIP star? So these 2 questions are equivalent, Searlson's and Kahn's, in the sense that a yes answer to one implies a yes answer to the other. And it actually takes a lot of work to show this equivalence. But a yes answer to Searlson's problem implies a yes answer to this complexity question. If all those quantum commuting operator correlations can be approximated in finite dimensions, it implies the existence of an algorithm to upper bound MIP star.
But there's some detail there, no, about like how the quality of the approximation, like somehow the quality of the approximation should depend only on like how high of the dimension you want to go, but not on the problem itself, or something. Or maybe not on the quantum correlation you want to achieve.
I guess it's just saying sort of that you mean Searlson's problem.
Yeah.
It's saying that if you take a commuting correlation, so this is just some conditional probability distribution, that's achieved in this commuting operator framework, can you find a sequence of finite dimensional strategies or operators that approximate this arbitrarily well?
But okay. What I'm confused about is why your result would say that that's not possible, because I would have thought it would depend on whether, like, maybe you can get to it, but you just can't get to it, like the dimension you have to go to get close to it is sort of arbitrarily bad.
Right.
eventually you will get close, but just
Right. So. So I mean, here I'm not even concerned with complexity. I'm just asking for any computability, up or down. So if it turns out that all of these computing correlations could be approximated, I mean, at any rate, then it would mean there is an algorithm that can search over these finite dimensional strategies, and then there's another algorithm that provides certificates for upper bounds, and these two will eventually converge if Sirelson's answer has a positive, the question has a positive answer. Yeah, maybe I'll explain offline. Well, anyhow, through these connections, by proving a sort of an algorithmic no-go result, implies no to Sirelson's problem and therefore no to the Kahn embedding question. So that's all I'll say about that. Let me come back to this multi-prover lens. It's really a wonderful conceptual framework to think about many different problems. And I think part of it comes from the fact that there's a very operational view. We think of these provers as trying to do something and operationally and so on. It's very useful. And the central tool in thinking about this is really these rigidity tests. This is guiding us a lot. So that's all.
I think that physically it's unlikely to be that in this real physical world, real physically realizable MIP stars would let you do RE. So what part do you think would fail first?
You mean what would prevent you from running a physical experiment based on this?
Yeah, I don't think it's likely that the physical world, that if I wrap on the table or the two entangled tables in the right way, it'll tell me whether something will halt.
All right, so what will fail is just running out of the number of qubits in the universe. So, or put another way, if you wanted to certify that a computation halts in time t, then what would the provers have to do? They would have to share log t qubits, roughly speaking. So if t is not too large and you have enough access to entangled qubits, in principle you could run this experiment. What this is saying is that for any t, there could be provers that share, if they had enough qubits, they could prove to you that this Turing machine halts in time t.
But you needed more than just entanglement. You were giving the provers a lot of power, arbitrary power. If I didn't allow you that, how far would you get?
As much power as you're willing to give to these real-world devices.
Let's say arbitrary quantum computations, but in a real, like a circuit model. So, is it really constrained by the amount of entanglement that's available, or is it constrained by the local power of the provers?
So the amount of entanglement and the amount of power needed for the provers is roughly the same. So if you need t qubits, then they roughly need poly t quantum computational power to run this.
Do you need quantum computation or is classical computation underlying that? Because as far as I understood, we just pick questions and then do the classical thing, right?
Yes.
Okay.
Well, they have to do these Sure. Okay. In terms of actual, what quantum abilities they need, they just need to measure single qubit x and z, and then do classical processing on top of it.
They don't have to do basis changes?
No, just x and z measurements.
Interesting.
Question with, the introspection protocol describe it required multiple provers, right? Is there any possibility if you only have a single prover? I'm just wondering that if a single prover with quantum capabilities, like having just quantum information, and you have some sort of notion of introspection protocol for just a single prover in isolation. I'm not talking about.
That's a good question. say you're willing to assume crypto assumptions, like in Irma's protocol. Well, actually, there was a paper a couple of nights ago by Thomas about using just a single prover. You can in crypto.
Thinking, could this be another way of just getting that? Because that would mean that maybe if there's a single prover that can do this, and it's sort of like not a round reduction, but it's sort of doing something like it's sort of like a round reduction protocol, right? This introspection protocol.
Yeah,
just trying to.
Well, I guess it's more like the number of rounds are the same, but you're shrinking the messages. Seems like you can do something.
If there are no more questions, then let's thank Harry again.